In this recording, I'm going to be looking at this section over here, define magnetic field and magnetic flux linkage. This term magnetic flux and magnetic flux linkage was introduced because it was seen that it's not only a matter of the strength of the magnetic field, the B, but also the area over which the B operates gives an indication of the strength of the induced EMF. Now, to discuss this in a little bit more detail, we are going to just call up the app that we have used before, this one over here, and you can see I've got the situation of this coil. I can actually increase the loop area. Now I've got to try and do this so it's a similar speed, but if I move this to and fro, I am causing an EMF, a voltage here, to be produced in this coil. Now, if I increase that area and I move it now, the voltage that I produce is actually bigger than with the smaller area. It's not only the strength of the magnetic field, but also it is the size of the area in which the magnetic field operates that will influence the voltage that I have. So going back now to my textbook, the textbook that you use, we can use this to further explain it. Now, this is a symbol that we use, this phi, like that. This is for the magnetic flux. And it's a combination, as you can see here, of the B and A. I'll write this bigger, that phi is equal to B times A. Obviously, the bigger the area, or the bigger the magnetic field, the stronger the magnetic field, the greater the magnetic flux. Now, there's a further addition to this formula in that it's not only equal to that, but it's also dependent on the angle that the magnetic field makes with the area in which it goes through. Now, if you have a look at this situation, this is the area here, and it is basically at right angles, so all the magnetic field is going through this area. Now, this angle theta is actually the angle between the line that is drawn at 90 degrees to the surface. So if this surface here, that's an angle 90 degrees, and if I draw that angle there, it would actually run along the magnetic field line. The angle between the magnetic field line and this line would actually be 0. Here it's at an angle here. This is our angle theta. This is the line drawn 90 degrees to my surface, to the surface, and it's making this angle. Now I think you hopefully can see that as we move this around, so maybe as I make this angle 90 degrees, let me just get rid of this. As we make this angle 90 degrees, this theta 90 degrees, would actually get something like this. And all the magnetic flux going through here won't actually go through that area. So there'll be 0 magnetic field going through the area. And that's why we use this formula, phi is equal to BA cos of theta. Obviously, when theta is equal to 0, the cos of theta is equal to 1, and therefore we get phi is equal to BA. We get a full amount, and when theta is equal to 90 degrees, the cos of theta is equal to 0. So it actually cancels each other out. So this phi gives us an idea of the amount of magnetic field that is available for production of EMF. We sometimes also call this magnetic flux linkage, because basically we're getting a linkage with an area, the amount of magnetic field that is being linked through an area. And we are going to use this term, this magnetic flux, this phi, in some further formulas that were developed by a person called Faraday, which I will discuss in the next training, the next discussion.